So you can hear my voice clearly, yeah? I hope.
Yes. Yes, doctor. We can hear your voice.
Okay. Can I will just share my screen and then continue with my introduction. Um, a minute, yeah. This one. Put the sound. This one. And I hope you can see my screen.
Yes.
Yeah. And it's the other way around. Okay. Okay, as I said before, I was one of the lecturers at UTP teaching this process integration Masters of Science program a couple of years ago, and then I moved to work in the industries again, and um, I'm now here invited to share something, and then so that it becomes like our lessons learned, and then yeah, I mean. As one of the, I think this course, refiner optimization is not the core course as far as I can understand. It's like um, optional course, like you have to either you can take it or not, right? Something that you chose to, and the um, the course names itself says it's refinery optimization. So I put here introduction to refinery optimization. You can see my pointer. So I put here introduction in the beginning because it's impossible for every one of us to really be able to do refinery optimization within like a semester or so. So what we are going to share with you is like an introduction. I will start with what is refinery, and even though I think there is also like a refinery and petrochemical course that you may or may not have taken before this course, and then that's I will share a little bit on that, touch a little bit, which is today. I will show you the schedule as well, and then the optimization part. So I'm here. You have to have these the core course of the optimization because it has to be done before you can take any of the electives. So I'm hoping that you've taken this optimization course and then feel confident that you can do it to some extent. Yeah, basically. So I will start with the refinery and then the optimization and so on and so forth, and then I will show you what we're going to do. As mentioned, think I will just go through the slides. These are some of the references which I think in the short time period that it's good to go through them, and then if you can then yeah, I mean good to go through them. I find them very valuable, and then if we look into the refinery as a whole, so we have to look into the refinery value chain. So what I mean by that is that the moment that we get our crude oil, so where's my pen? So the moment that we get our crude oil, and then we ship it to different locations, and we purchase it from different location, and we ship it to our storage tank in some, I don't know, maybe in Johor Bahru or in Malacca or in Kerteh. um, and then we have like we may or may not have like a charging tanks, and then we send the crude to the CDU, crude distillation units, which is then the first step into the in the refinery. And then we have also the other unit operation, and then finally the tanks, the intermediate tanks, and then we have like a blending operation so that we can blend all of these streams into products that meet the specifications required by either government or the industry's needs. And then we then distribute them from our refinery. From our refinery, we distribute them to terminals or gas stations or whatnot. So right from here, from where the crude oil is being purchased up until the gate of the refinery, and then within the refinery, and then all the way until the customers basically. So this is what we call as the refinery value chain. So throughout my slides, I'll be taking snapshots of figures, which I take from the one or some of the references that I mentioned previously. Um, what people do, or they characterize this refinery value chain into several steps. So what they call here is then the planning and scheduling for crude oil movement, and there's also another planning and scheduling for the product blending and distribution. So yeah, there are two: planning and scheduling, which is then the upstream, very upstream on the crude oil, and then planning and scheduling of the downstream, which is then the products. And then in between we can have like a blend of the crude assays. So because we may have different types of crudes, and then our refinery is just like it's one type of refinery, right? It doesn't change, and that refinery was designed previously to cater a certain type of crude oils. So if we happen to have some years later, if we happen to have different types of crude oils, we may need to blend them to match what we need to produce, and also to match what we can process. So these two things, yeah, to match what we can process depending on the refinery configuration that we have, and also to match what we want to produce or what we have to produce depending on what type of company you are. And then in between also we need to optimize the units and processes. So there are four how do I call it? Four basically rough, yeah, from this diagram. There are four types of optimization. Number one is that we optimize the planning of the crude oils, and that's this number one. And then the number two is that we optimize the blend of the crude oils, and then number three is that we optimize the unit processing in the refinery itself, and then number four is then the blending, and then the planning for the products distribution. So these four, in a nutshell, yeah. So we will be learning with more deeper in some of them, and then less deeper in some other part of them, because we will have a very limited time frame to go through this, which I don't think it's going to be very practical to deep dive into each of these topic. In the plant, there are like a plant decision hierarchy, what people say. So we have a planning team. A planning team means yeah, what we want to make in weekly basis. And then once we know, so this week we're going to have crude A, for example, from I don't know, country A, and then the crude B from country B, and then we're going to mix them together, and then we're going to make this amount of gasoline, that amount of diesel, this amount of jet fuel, whatever. Yeah, so that's what that's what they're going to say here in the planning department. And then they base the decision based on the crude price, based on the plant capability, and based on the product's prices. Okay, so once they say so, and then that decision goes to the scheduling department, and then they will then tell, okay, so we are going to make more gasoline these days and more diesel that days, or whatnot. We're going to use this crude or that crude. We're going to empty this tank or that tank. So depending on the what is happening on the field, they will then make the scheduling. And then once they know in days, they put that crude into they charge the crude into the plant, and then that plant, as we know it, because we are all process engineers, then we will then try to maximize or optimize, in this case, maximize the profitability of the plant in hourly basis, what they call like real-time optimization. So basically what we have here is that we have a plant model, which I'm going to use this as your project for this course. So you have to make a plant model. So from this plant model, they will then use the plant model. They will take the data from the plant, by whatever means, depending on the company. And then they will then use that information from the plant as an input to the model, and then that model is then going to be used to maximize the profit. So there we have already like economic calculations in that model. They have all the cost data in that model, and then they can run it. So once they run it, the output of that particular model is typically like a set point. So so that flow rate should be that reactor should be run at a certain temperature, a certain flow rate or pressure or whatnot. So it will then, that information from the real-time optimization model, it will then be sent to the plant, either online or offline, or manual or automatic. Yeah, it really depends. And then you'll get, hopefully, you'll get the plants running in optimum way. And then once that become the set points, and then it's then a matter of the specific unit operations to be able to make sure that that unit is able to to be controlled, or to reach that set point. So that's why the MPC is over here, the model predictive control. And then it goes to what we know as a BPCS, the basic process control system. So so from here to there is what they call like this plant decision hierarchy. This is more like an offline, so that's why they put like the dotted lines. And then this is more like all connected, because these are all in the plant. Yeah? These are all in the plant. This can be also disconnected or manual, but these are typically already connected. So these are all in the plant, and then this like still ad hoc basis. But you can, I think, in the coming years or decades, with more and more technologies advancement, we can see this more and more often. I'll spend some time here. I don't know if you can hear this. Can you hear the sound?
Yes, yes, can hear the sound.
I'm not well, I cannot remove this part, so it's just like a video that I took here from the internet, so forgive me for that. Just to give you an idea.
Refineries typically run on low margins. Fluctuating market conditions can make refineries more vulnerable, which is why profit margin analysis is crucial. AspenTech enables rigorous profit margin analysis through a refinery-wide process model. Equipped with this model, process engineers can now determine specific areas in the refining process where profits can be improved, find alternative methods to improve profits, as well as predict and compare the impact of each alternative and recommend a solution. Let's take a look at some of the challenges with rigorous refinery-wide models. Rigorous models are cumbersome. They take a long time to develop and run. This model complexity demands a high level of expertise with the process simulation tools to both develop and use. Because of this demand, refineries are forced to stay dependent on expensive third-party consultants to both make and use this type of model. The AspenTech solution for developing a refinery-wide model leverages the integration between Aspen PIMS and Aspen HYSYS. Step 1 is to reproduce the refinery-wide PIMS model in HYSYS. This is easy to do with the shortcut petroleum shift reactor models included in Aspen HYSYS. These models are an exact replica of the reactor representation used in Aspen PIMS. At this point, the model developed has the same level of credibility as that of an Aspen PIMS refinery-wide model. Step 2 is to selectively upgrade specific shortcut submodel units to rigorous models. Doing this will enhance the accuracy of the refinery-wide model. This gives users the flexibility to prioritize and select unit models that can be converted to rigorous models and to have control over the level of rigor. With V8.8 of Aspen HYSYS, a complete set of rigorous reactor models are available. In Step 3, the refinery-wide model can now be used to conduct profit margin analysis of the entire refinery and to plan next steps to boost refinery profits. The AspenTech solution of a refinery-wide model is a mix of both shortcut and rigorous models. This keeps the model manageable and accurate. Now that the model has been developed, the process engineer can find specific areas in the process where improvements can be made in order to boost refinery profits. For example, the process engineer identifies that there is an opportunity for improvement in the vacuum distillation unit. More specifically, the cut points set for the vacuum resid stream is low. The process engineer can then try alternative solutions to address the low profit margin. In this example, the engineer can try raising the vacuum resid cut point temperature from 1025 degrees to 1050 degrees Fahrenheit. The process engineer can then predict the impact of the solution on refinery profits. In this demonstration, raising the vacuum resid cut point temperature has resulted in an overall profit increase from a negative 29 cents per barrel to a positive 24 cents per barrel. The refinery-wide model can be used to analyze profit margins from capital projects such as refinery reconfigurations planned to tailor to the different crude and product mixes, to evaluate the economic feasibility of operational improvements such as a change in the catalyst for the FCC unit, to determine operational responses for unexpected events such as a breakdown of a key feed pump, as a central repository of all Aspen HYSYS-based planning model support tools. Refineries can maximize profits from analysis using a refinery-wide process model in Aspen HYSYS. Aspen technology can deliver a model which is quicker and easier to develop, faster to run, and highly accurate. Learn more by visiting.
Okay, so that's enough for the commercial. I'm not promoting that product anyhow. So I just like to give you a glimpse of what people do in the refinery in order to try to keep up with the current stringent regulations, with the current pressure on the prices, and then and everything else on the demand as well. So so to get these activities, so now you understand, I've shown you what needs to be optimized, and then I've shown you what are the that plant decision hierarchy, and then now I need to say this because I took this from one of the references that can go back and read. What we see is that to be able to enable this kind of plant-wide refinery optimization, so all these concepts can also be applied into all kinds of processing facilities, not only refinery. So what they need to have, or what they typically have, is that company has like a strong engineering center and a clear technical career path, because if it's not clear and then people don't want to go there, and then people then say, well, there is no remuneration or benefit for me, why should I go and work in this kind of department, for example. And then there's also like we need to have like a strong collaboration with the other departments as well. So you can see that we're working with that planning department and then scheduling department, also with the operators on the site, and also with the maintenance people, because they can tell you when they will do a next overhaul or whatnot. And then we also need to have like a very reliable platform for the data to be transferred from one discipline to the other discipline, from one department to the other department. And then lastly is that you need to have like because this is not like a one shot once a day or once in a few weeks or whatnot. So it's like years of work in development to make one model of a unit operation, and then make another model of unit operation, and then integrate them together. So you make one unit, and then you make another unit, and then you make another unit, and then you can then have like different types of feeds. That type of feeds, like feed B, and they will then go to this and go to there. In the end, you will have like a product which you can then sell. So all of these activities, it takes years in developing progress. So so I'm now very sensitive. So what I propose, so we have 7 weeks of lectures with me, and then you may have some other weeks for exams with Afik and Chongyang, and then during these 7 weeks, so this is then our first week. We'll be having like a regular 2 hours per week, except for maybe next week we'll have like 3 hours. So I put that 3 hours because we're going to touch again a little bit on the optimization and then linear programming. So I think 3 hours may be sufficient. I know that you have taken the optimization, so in that sense we may not need maybe these 3 hours, but we'll see. I'll give you some. We'll do some exercises, and then if we at the beginning of the class, if I see that you cannot really. If you have some struggles in that, and then we may have to use the 3 hours. And then the third week is then we will discuss on the process modeling and optimization. So this one is not going to be like a lecture. It's more like an introduction to what you're going to be doing for the next 1, 2, 3, 4 weeks as part of your project, maybe the 5th week next week, as part of your project. Yeah. So there are some marks on that project, and then I expect you to be able to make a plant model. That's number one. So you can use Aspen Tech product or Schlumberger product symmetry. We have both simulators available in UTP. But since you are all open online, I mean it's a ODL basically. So I don't know how you can manage to get that kind of software. So it's all up to you. Yeah. So these two. So so make that simulation. I think I will have something after this, and then and then the next week is that the hydrogen. We'll discuss on the hydrogen, and then the RTO, the one that you just saw briefly, and then refinery wide optimization, what it means by that, and then lastly the supply chain optimization. So the supply chain again that includes that the planning and scheduling for the crude oil, and then planning and scheduling for the product. So that's basically what we how to call it, yeah, traditionally called as like a supply chain optimization. So the rest, so what's happening here is more like this is more like uh, this is more like so this is more like internal refinery, internal yeah, this is internal, and then this then going to be like an external of that refinery. Yeah? You know that this is a refinery. So you have crude oil, this then the product, so this then your supply chain traditionally. So we'll do the traditional way. And it's very sensitive. That's one. We will, because this class is like a Saturday afternoon, so to avoid it's also like after lunch, yeah. So you are very much welcome to ask questions during this the sharing session that we having. So just interrupt me, and then I'll maybe put a question in the comment, and then later on maybe Afik or Chong Yang can help me or interrupt me to read out loud this question. Yeah, so we could do that as well. So my intention is that so that you can have something tangible by the end of these 7 weeks, so that you can then come back to your plan, say to your manager that you can do some kind of optimization. So that's my practical objective, you know, from this class. Yeah, I don't want you to just glance through this class and then you get some marks and then you graduate and then you're happy, but then by the end of this program you still cannot do this. So I don't want that to happen. Since this is this is an advanced course for Masters of Science in Process Integrations, which is very chemical engineering. So I assume that you have already taken this basic optimization class, which I think you have done so in the course, right? I think you have had it. Let me know if you haven't. But I'm only assuming, yeah. So my assumption can be wrong. So I'm assuming that you have this basic optimization, and then you know a little bit on the engineering economics, process engineering economics, like I used to call it. So engineering economics is basically that you know from that plant, if we want to calculate the economic benefits of a modification in the like a physical modifications in any plant, yeah. And then you know how to calculate that, you know how to evaluate the profitability of that approach. That's something that I'm assuming that you already have it. And then again, like I mentioned, this is a very chemical engineering. So I assume you must have already some organic chemistry background, because we'll be seeing those types of things in a few minutes. And then some reactions engineering knowledge, and then chemical engineering unit operations. So I hope that you know what it means by reactor, by distillation column, by catalyst. So I hope that you know all of these terms. And then I hope as well that you have already, or if you don't, you start learning something about that, about plant modeling and process simulation. Yeah, there are plenty of YouTube's or documents or whatnot, or books that you can learn, and then you can then try it on yourself, because this is going to be part of your project. So you have to be able to do or model and simulate a certain part of the plant at least. And then the data analysis. This is not what typical. It's not in the typical or conventional chemical engineering curriculum, but then it's going to be added soon, I guess. So three of you are practitioners, right? So you have seen data, so I hope that you can do some type of data analysis, and then with that you can also do some regression, at least using Excel. Yeah, data analysis and regression using Excel. And then lastly, hopefully you can do some programming, because we are going to need these four skills in the project. Yeah, we're going to need these four skills in the project. So, but don't worry, you have a few weeks to go, and then in the meantime, you can then simply build up your skill and the knowledge, and then while doing the project, you can always discuss it with me or with Jongyang or with Afik as we go along. So, talking about the case studies. So, these case studies, what we're going to do, So what we're going to do is that we're going to do refinery modeling and simulation with surrogate models for optimization. So what I mean is that you can, like I said, yeah, you can either use HYSYS or Symmetry, and then the Excel solver at least. So these are the tools that you can select from, and then you can take either find somewhere an existing refinery wide model, or if not, then you have to build it yourself. So you can build a refinery unit, not the whole refinery actually, just like an FCC type or hydrocracking or hydrotreating. What I put over here, we will learn what this means later on. Or at least if you can't find one, or it's too difficult for you, you can at least make a model for plants, chemical plants, but it has to consist at least one reactor with the kinetics, and then a distillation column. At least one reactor and one distillation column. These two, for the sake of at least to get you the skills, so that I can say yes, you get the skills already. So this, so either you find somewhere refinery model, or you find as well, or you build yourself some a refinery unit, or you can then make your own model consisting of at least a reactor and a distillation column. Okay. And then you need to understand, for that particular plant model that you have, you need to understand what are the independent variables, or what are the X or variables, or what are the, what do you call it, things that you can do and control or manipulate in the plant. Typically we have in the plant, you have a control valve that you can open and close. So that particular control valve that you can open and close, it must have it does something with the flow rate, it does something with the temperature, it does something with the energy, and so on and so forth. So understand the key parameters of that independent variables in the plant, and then to achieve a certain objectives. So for example, if you want to increase the yield of the reactor, for example, so yield becomes the dependent variable, one of the dependent variable. And then what you need to do, maybe you need to increase the temperature, the fit in the temperature, or maybe you need to increase the cooling medium, or reduce or increase also the heating medium, or whatnot, depending on the plant that you have. And then based on these independent and then dependent variables, so I want you to get at least 2 dependent variables. Well, we'll see as we go along, 1 or 2. And then you do like a sensitivity analysis of the X values and the Y values. So all of this is done in that process simulation software. And then you make regressions based on the X and Y. So this regression can come in the forms of like a linear regression or non-linear regressions. Or if you are, there's also very good in programming, you can do like a neural network type of decision tree type of regressions. It's up to you. At least we need to have like regressions. So assume that you have like a linear regressions, And then you can then you can use that regressions to optimize the performance of the your selected Y for that plant. Okay, so once you get the optimum X from that optimization exercise over here, and then you will then apply this X in back into your plant model. Because that plant model becomes as a real plant for you. Yeah, because we don't have actual plant data or any plant that you can play with. So these models that you make, becomes your actual plant. See, the model that you make over here becomes your actual plant. And then this then your analysis, okay, and then this then your optimization, and then this then how you validate. So you put that optimum variables, the X variables that you obtain from here, and then you put it back into the plant, into your process simulation model, and see if the optimization that you do over here confirm exactly what the plant would do. Okay, so that's the case study that you're going to do. So it will be you can start now by finding what type of unit operation that you would want to do, or by getting skills in making process in using the process simulation software, or anything else. Yeah, anything related to everything that is related to this task. So until here, is there any questions? Otherwise, we can go to the next for the topic for today. Basically, this is just like an introduction. So, do you have any questions for the case study, for the schedule, for what else? Yeah, the schedule, the case study, and then the topic itself, like this, and then the references. Any question? No question. Okay, very good. If there's no question, discuss. Now I have okay, yeah. Just let me know if you have any questions. So introduction of Refinery. So we have like a 1.5 hour, basically, less than 5 minutes, less than 1.5 hour. So I don't think let's be practical over here. So refinery processing covers a lot more topics than what we can cover in one semester even. So we are now trying to condense that 1 year or one semester study into 1.5 hour. So let's be practical. I will emphasize some of the things that I think very important as an introduction, and I will also skip some of the things that I don't think it's very relevant at this point in time. But you have already the slides, right, uploaded in YouLearn, which you can always come back, and then this course this lecture is recorded as well. Main references, yeah, you can go. It's the same. Some of the main references that I mentioned before. This is a good one. This is also a good one. So you can read this first, and then you can also read this. So that should give you a boost in understanding what a refinery is all about. And then this is more like if we can integrate that with petrochemical operations, which we now which we are now seeing more and more, yeah, compared to the conventional refinery. And then this is the I think I don't know if you have this slide, but this is what the heritage course that we have since 2002, so exactly 20 years ago. Um, the one that you have in the YouLearn, I flip it around this just a few hours ago in such a way that I want to emphasize something more. So we'll talk about the feat of the refinery, and then how is then the refinery configured to process that feed and then to produce some of the products. And then well, this is, I think we can skip because it's the same. Yeah, refining economics, chemical engineering economics, or engineering economics is just the same. And then if we still have some time, we'll go a little bit deeper on the how do people characterize the refining streams. So how do we characterize it? Because unlike chemical engineer or unlike like a chemical plants where we have, for example, we have A plus B. Let's write this. So we have A plus B makes C. Like for example, if you have like a 2-methanol and then you dehydrate that, so you get DME, and then you get water. So these are like exact component, yeah, the exact component. But that is not the case with refinery. No, very I mean, yeah, it's not exactly the case with refinery. Um, so if we have some time, we will then discuss about that. And then there are two approaches that people have been using and developing and using. The first one is then the easiest one or the old one as well, the lumping models, and then the second one is then the more sophisticated approach with the more sophisticated technologies to characterize the stream. Then they call it like a molecular models because we could see literally to the down to the molecular level. So feed characterization. We start with this. We have a crude oil, typical refinery here, and then from this crude oil we go to the what they call like a distillation unit. And then as we know in the distillation unit we separate things based on the well we say it's a boiling point, but then basically it's based on the how do you call it, the easiness of the volatility index. So that's basically the correct term. So we separate them based on their volatility. So so the lower boiling point means they are more lighter. Yeah, low boiling point they are lighter, lighter, and they have a very high volatility. Yeah, low boiling point, lighter, and also high volatility. So on the contrary, the component at the bottom is what we call like a high boiling point component. They are heavier and they have the very low volatility. So typically the boiling range is about this. So this is I take it from here. It's actually the products are like very much overlapping to each other, but typically from the crude distillation unit we will get this kind of cut, basically, which you can adjust to some degree. So lighter than 85 degree Fahrenheit, which is like a butane, and then lighter than butane. Butane is C4. I put the degree C next to it so that we can have a feeling, because here we don't use Fahrenheit, we use degree C, use Celsius. And then the heavier than the light gases is what we call like a naphtha, and then it also include this. We use it to blend gasoline. So here we have like a maybe light naphtha, if you want to call it, and then this is what we call like a heavy naphtha. And then it's also like more. I prefer to use this degree C, so around 80 degrees C until 160, 170 degrees C. And then we have also overlapping with that on the above 150, 160 degrees C is that the kerosene and jet fuel, and also a little bit of diesel. And then heavier than that, we have like heating oil. So the fuel, heating oil, what they call. And then we have like a heavy oil or heavy gas oil in the range of 340, 350 until 500 something. And then above 500 degrees C, we call it typically like a residue. Yeah, we call it residue or atmospheric residue. Yeah, atmospheric residue. And then that's another simplified refinery. So we have this then the atmospheric distillation column. So all the crudes are coming into here. All the crudes are coming into this atmospheric distillation column, and then the heavy part, like here, this heavy part, it goes to what they call vacuum distillation unit. So that vacuum distillation unit here in this diagram is just next to it. So the heavy part down here goes to this guy. Yeah, it goes to this guy. So if I may so the heavy part goes to this guy. Okay. And then there are many streams going out. These are simplified, and then it goes to that naphtha. So we have a gas. So this gas is going to be burnt, or nowadays we don't want to burn it. We try to keep the make useful some of these components as much as possible. But in the old refineries, or the conventional refineries, they're burning it. And then the second, the higher fractions of that goes to this naphtha hydrotreater, and then reformer, isomerization, and goes to the blending section. And then heavier than naphtha is then the kerosene, and then the jet fuel is over here, and it also goes to the blending. And then the heavy part of the goes to the vacuum distillation unit, and then it creates some of the feed to the fluid catalytic cracker or coker or whatnot. And then they have like hydrotreater, to remove some of the unwanted components. And then all of these products, they go to many tanks, so that after that tanks, they can then be blended to meet specific requirements or characteristics that the markets or the governments or regulations need. Okay, so this is like in a nutshell. And in a block diagram, what they call like a modern refinery. So in this book, modern refinery, so we have a crude oil, and then that crude oil goes through series of heat exchangers, and then we remove the salt. It's called desalting. So we remove the salts of this crude oil in this electrostatic precipitator, and then after that we have another series of heat exchanger to increase the temperature of this crude oil from ambient to a certain degree C as much as possible, and it goes to the furnace of the CDU, the crude distillation unit, or the atmospheric distillation unit. So we have a furnace over here, and then it will then just simply split all of those components, all of those splits basically and components. So the gas goes to the gas separation. We have these gas plants where they can also make LPG, whatnot. And then we have the light SR is a straight run naphtha, so it's light naphtha, heavy naphtha. I don't know why they call it straight run. Maybe it's a straight running from the atmospheric distillation unit. Maybe that is. And then we have heavier than the naphtha is then the kerosene. So I'm repeating this again so that you can have you can memorize it easily if you don't have any prior experience with refinery. And we also like a distillates after the kerosene, gas oil, and then what comes at the bottom, that 500 degrees above, it goes to the what we call like a vacuum distillation unit. Yeah, so these streams, they go to their respective units. So this guy in this particular example, it goes straight to the blending system, and then the heavy naphtha, it goes to the hydrotreating, and it goes to the reformer. So the goal of this reformer, as we will see later, is then to make or to increase the octane number of the product. Yeah, we will see later on. And then this kerosene can also directly goes to the jet fuel blending or something. And then this middle distillate, they can also crack it into to make some gasoline as well, or they can just also crack it to get some more diesel product out of it. So depending on what we require or what the economics that we can get, yeah. So are we more profitable by making more gasoline, or by making more diesel, or by making more jet fuel, and so on and so forth? So these are the things that we have to consider on that planning basis, so that we can always make the refinery run at its optimum profitability scale. So the same goes with the vacuum. So why we call it vacuum? Because the temperature over here out of the furnace, it's about 330, 340, 350 degrees C, depending on how what the type of crude that you have, and then how you want to operate that. Yeah, typically around that numbers, so 340 until 360 degrees C. So we cannot increase the temperature much higher than that, because we will then crack. What it means by crack is that you have a long molecule, and when you crack it, just like you break it down to a lighter molecule. So if you in here in this unit, we don't want to have any crack or any coke. Yeah. So here we just want to just simply split them once we get the energy from the furnace, and then we can just simply split them in the distillation unit. So we don't want to facilitate that cracking. Hence, for molecules heavier than that 360, 350 degrees C, we want to preserve them not to be cracked. We just want to separate them at a lower pressure. Yeah, remember that McAfee diagram. So you have this McAfee diagram. So typically you have something like this at a certain pressure, and then if you erase. So in the McAfee diagram, you can see just quickly. So I hope you know what this means. So this is then your your VLE column. So at a certain pressure, you get this, or at the ambient pressure, you will get this kind of graph. And then at the vacuum distillation, because you lower the pressure, that means you will then have you will then allow the compounds to have more space in between them. So that graph, this VLE graph, becomes something like this. Yeah. So it will then easier for you to separate them into just to split them. It will be easier compared to at the ambient pressure. So that's why we do the we do the vacuum. So with this vacuum, we can still operate them at the same range of temperature. But then we will then get more products out of that. Yeah, we'll get more what is remaining of this naphtha, kerosene, distillate, and so on and so forth from this vacuum distillation unit. So from this vacuum oil, we call it, so it can go to catalytic cracking, and then it can go to all kinds of units. In the end, what really matters is that which product that we are going to produce more, and then which unit that we are going to force more, and then how we are going to run each of these units. That is what we're going to see in this course. That's what we call it. That's why we call it refinery optimization. Any questions so far? So well, I see that you all understand this, so I can just go very quickly. So the feed into the refinery. So crude oil. There are several types of characterization. So one of them is what we call. I think it's one of the advanced one of the latest approach is that we call them like a piona. So I straight to this piona. Yeah. So we call it like a paraffins, isoparaffins, olefin, naphthenic, and aromatic. So this is where your organic chemistry comes in handy. So paraffin is something that is very straight line. So paraffin is a straight line. So things like this normal butane. So all of these alkanes, normal. So these are all paraffins. So from C1 until C100, if you want to call it, if they are all in like a straight line, they are all paraffins. And then isoparaffin is something that you have a branch like this. So in this case, it's isobutane. So 1, 2, 3, 4 isobutane. So you have a branch like this. That's what we call isoparaffins. Okay. So paraffins, isoparaffins, obviously because of their molecular structure, they can have, even though they have like the same carbon numbers, they may have different properties. Yeah. And then the third group is that what we call olefins. Olefins is something that we have to look at double bond. So these double bonds. So these double bonds, they call it olefins. And then we know it like alkene. So like ethylene, propylene, butane, and so on and so forth. So it has this double bond. I put ethylene and propylene here because these are two important feedstock for petrochemical, as an example. And then the naphthenic is what we call like a cyclic component. So this is like this. So pentanes, it's also like a pentanes. So cyclopentanes. So all of this cyclic, if it's a cyclohexane, cyclopentane, cycloheptane, and so on and so forth, these are all naphthenics. And then if we have a cyclohexane and then it has double bonds, so it has double bonds over here, over there, and over here, and that double bonds are moving. Yeah. And then that creates this what we call aromatics. We call it aromatics. So aromatics, the most important of them are BTX, so benzene, toluene. So toluene it says toluene because it has this branch. Just to recap, yeah, I'm just gonna go too quickly. without the branch, it's benzene. And then we have styrene, we have also BTX, so benzene, toluene, and then xylenes. So there are three types of xylenes. We can see two of them, like auto-xylenes, and then the para-xylenes over here. So this is auto. So if it's a para, it's a 1, and then another one is over here too. If it's meta, it's 1, and then another one over here. So this one is not stable, so hence it either go that way or this way. So hence we see mostly either auto or para. But these three, these three, benzene, toluene, xylenes being like an auto, meta, para. So so there are 5. Basically, these are also together with the ethylene and C2 and C3. So together with these they form the basic feedstock for petrochemicals. So with this piona, it's one way of characterizing the molecules that are available in the crude oil. And then another way to characterize it is then the people can then see, well, analyze how much then the carbon composition, like in this case about 80% or something, and then hydrogen. So we call it hydrocarbon simply because these components, they consist mostly of hydrogen and carbon. That's why this hydrocarbon terms comes into picture. And then we have also like sulfur, nitrogen, oxygen, and metals. So these are impurities. We don't want this. Yeah, what we want is only the hydrocarbon, or the carbon and hydrogen, because this hydrocarbon, it can then becomes our gasoline, the diesel, fuels, and so on and so forth. And then these are all these impurities. We don't want them because they are harmful to the engines, they're harmful to the environments, and then they're also harmful to us. So we need to remove them in the units called hydrotreating. Yeah, that's why you see in the refineries there see plenty of hydrotreating, either very so and so hydrotreating into like deep hydrotreating. So these impurities, as I mentioned, so we have sulfur. So I just put here as a name. And so sulfur. So here, if it attached to the primary C, yeah, I say it's primary C. If it's attached to the primary C, we call it mercaptan. And then if it's like here, it's also like attached to primary C, it's a mercaptan. And in this case, it's like a thiophene. And then the heavier the splits that you have. If you remember that the crude oil goes right from the light to heavy. So the heavier it gets, the more this S into like the very difficult situation. So you have like here you have like what is it? Yeah, it's very okay. So you can see here the aromatics. So you can also have like a polyaromatics. So you have many aromatics, and then in many cases where you have the heavy part over here, so this guy is trapped into those aromatics and polyaromatics structure. The same way with the oxygens, nitrogens, and then heavy metals. So the heavier the fractions of the crude oil, the more these guys are being trapped into the aromatics part of the crude oil, the more difficult it's going to be for us to take that out. Yeah, the heavier the products, the heavier these products, and then the more difficult that for us to get this out of the system. So that means we will need to have more energy to get them out, more advanced technologies to get them out, and then to clean the fuels. Okay, so that's why if our crude oil is very what they call it, like a very sweet and then very light, it's very easy to process. Yeah, we could get like more gasoline, more fuels, but it's also very expensive because well, it's expensive because there is a very minor operating cost necessary to process them. But then for heavy crudes or very dirty crudes, we will need much more operating costs to treat them, and those kinds of crudes are relatively cheaper. So the crude assay, let me know if there's any question here. I'm not going to talk for 2 hours, but I can. But if you look at this, so these are typical crude assay. If you go to yeah, I will show you in a minute where you can go to get an examples of this. So we have like a whole crude here. Just look at the whole crude, the first column. So it's 100% of whole crude. That's what it means. And then the API gravity is 38.6. So we'll go straight to the API. So this is the API gravity. API gravity equals to is then 141.5 divided by specific gravity. So the specific gravity, you know that this is that in relation to the gravity of water, right? So if the specific gravity is 1, that means that is then the density of water at 15 degrees C or 60 degrees Fahrenheit. So if it's water, that means the API is 10. Yeah? If it's water, that means the API is 10. So 141 minus 131, that's 10. Any crude, any light crude, it goes with the API of they put it here, larger than 38. It's light crude, and a medium crude is then from 29 till 38. That's a medium crude, and heavy crude is then from 8.5 to 8.5. So 8.5 is heavier than water. Yeah, means heavier than water means it will if you put this oil and water together, that oil will sink. So it's heavier than water, but then this is on the bitumen already. Yeah, this heavier than water is all in the bitumen and oil sands and stuff. So these are all heavier than water. So if we go back here, so this is then 38, above 38. So this is then considered to be light crude. So this light crude, we expected to have like a very minor amount, not very, some percentage of relatively low percentage of impurities, and then higher like light gases, naphtha, and all of those lighter products. So you can see now, so with this whole crude, they cannot analyze what the carbon and hydrogen is because it's too difficult for them. And then you see that the pour point is then the temperature at which that you will then start to flow if you pour it, minus 12 degrees C. So at minus 13 degrees C, you cannot pour this guy. So it cannot be poured because you cannot pump it. And then it has this 0.3 or 3000 ppms of sulfur in it. So it's quite light, right? Very low. And then nitrogen is then 900 ppm. This 3000 ppms. We have some viscosity over here. Centi-Stokes. We have mercaptan sulfur also in ppm. Conradsson carbon residue. Nickel, vanadium, heavy. This is the heavy metals. Conradsson carbon residue. There's this Conradsson guy. So he just, if we say, like for example, if you burn this sample, and then how much is then the carbon residue left in it? Yeah, that's it. So if I can explain it right. And they have like some tests on the heat combustion, salt content, and then it turns out that they cannot do like this paraffin naphthenics and aromatics analysis on this crude oil for some reason. And then they go more on the freeze point. There's nothing. Smoke point also not. C10 index, somehow they can do it. And then they do this. They do this experiment. This is the standard, yeah, D1160. And then they make this what we call like a boiling point curve. So this is then the initial boiling point, so they can measure that, and then this is then the end boiling point, or the EBP. So they measure like a 50% volume of this crude will evaporate when the temperature reach 51.9 degrees C. Yeah. So I repeat. So if 5% of this crude is evaporated already, so what's left is then 95% in the flask, and then that means that temperature is about 51.9 degrees C. So they increase the temperature, and then it will then evaporate more and more. Yeah, so they have this 100%. Then the heat they put heat here, and then they will then evaporate, and then they measure temperature over here. So if the temperature is then 160 degrees C, for example, and then and this guy becomes like 70% already. 70%. Yeah. So 30% is gone. Yeah, at this temperature. So that's what it means. And then they do the same analysis for all of the fractions. So they have this C4 and minus. So this is what we call like lights. And then this is then the light naphtha, the heavy naphtha. Is that the diesel, jet fuel, and then the oil, and then this is the heavy oil. It's very strange. This is also the heavy oils. These are all like heavy oils. This is what they call like how do I call it, yeah, the heavies or residue. Sorry, the residue. So if we see, say for example, we see this like light naphtha. So it's light naphtha is about, out of 100%, light naphtha is about 8.26% volume, and then the API gravity is 80, which makes sense, right? Because it's light. And then the more you go down, means the heavier you go, the smaller the API number. So you can see this crude is almost like water, so it's as heavy as water. And then the more you go down, also roughly you will have more and more carbons compared to hydrogen. So you can see that your hydrogen to carbon number ratio is going to be down the lower you go, and then the pour point is going to be like increasing and increasing. Yeah, I don't know what this means, but if you go here, you can see that it's getting thicker and thicker, and then you cannot pour it anymore at room temperature already. And then you will have more and more sulfur as expected. Yeah, just giving you the trend. Yeah, more and more sulfur, more and more. All of these impurities, they are going to be more and more, can be found in the heavier fractions of the crude oil. Okay. And then this graph, I think you can make this later on, or maybe after this. So you can plot this graph, and then you will then see, for example, like in this case, I would say just okay. So we have now this boiling point graph. So this then your crude oil. Yeah, assume that this is your crude oil. So it's from this from some degree C. Yeah, without the lights. Yeah, this is without lights. Because this is 100, because it's about 20, maybe 30, 20. This is without lights. And then go straight until here. So you can see it's the final boiling point is about 400 degrees C. So it's typically like light crude. And then if this crude is then being split up into the fractions of it, the fractions, typical fractions, yeah, from 20 to like 80 degrees CE. That's that's then what we call this. This is then light naphtha, right? So this then if this then 20%, so about 10% roughly. So 10% is then your light naphtha. Yeah, can you follow? Yeah, 10% is then your light naphtha. And then from this 80 degrees C up until 160, 170 degrees C, somewhere here is going to be your, I don't know, it's not looking nice. So somewhere here, this part, this is then your heavy naphtha. This is then your light naphtha. Can you follow? If not, then ask me questions. Yeah. And in here up until, I don't know, maybe somewhere here, this is then your like a diesel or jet fuel or something. So maybe let's take the 300. So somewhere here, this is then your diesel and jet fuel or diesel or kerosene, somewhere here. You can then so you can see this light crude, it consists majority of these distillate fractions, that the jet fuel, kerosene, diesel, that's distillate fractions as we call it, and then the heavy naphtha. So you can make more gasolines over here. So this type of crude, this example, this imaginary crude, is a very profitable in terms of a refinery. Not very profitable. It makes lots of products with that. Yeah, and then it's only like 10% less than 10% as the residue, and that residue can also quickly crack or I don't know, salt, or maybe it's only like 10%. Or maybe you can, if you have like a vacuum distillation unit, you can then also send it and then make some more naphtha and then the jet fuel. So this is then the typical I'll draw another one. So if we then in color blue, green. So this is how they split it into this is how they split it into I mean in that distillation column. Yeah, so we have like a light naphtha roughly, yeah, with this example, heavy naphtha, and then you have this jet fuel or distillate, call it just the common name, and this then your residue. So this guy, because the splitting in this distillation is not going to be like sharp split. It's not going. The goal of this is not to have like a perfect separation of this distillation. It's just to give you some splits. So there will be some overlaps in between of these streams. So the your light naphtha will be something like this, and then the heavy naphtha will be something like that, and then the distillate will be something like this graph, and then you will have residue something like that. Yeah, so something like that. Okay, and then if they plot the graph here just to give you an idea. So we have this API gravity, and then we have the molecular mass gravity. So if anybody can tell me which one is which, the solid line is API or molecular mass? Nobody? Okay, then I will say it for myself.
API.
The so as we know, yeah, you can see here to the right means the more you go to the right, that means the more heavy. I mean, you'll be then going to the heavier and heavier region, and then as you go to heavier and heavier region, the API gravity should be expected to decrease. Okay, so this is the API graph. This is the API graph, and then this is what they call like this is what the molecular mass. So the heavier it becomes, the more carbons in it, and then as we know that carbons is 12 times heavier than the hydrogen, so you will get more and more or higher and higher values of molecular mass. So this is then the molecular mass graph. Yeah, as the so we can, from this graph we can see the correlation between the boiling point, the split fractions that I put over here, and then the API gravity, the molecular mass. So there are many information. So from this graph, from this picture, you can see the boiling point, the split fractions roughly, the API, the molecular mass. So these four informations are there, and then you can then tell how much profit that you can gain. Yeah, roughly speaking. Okay, because you know, if you know this, you know the price of gasoline, then you can then calculate how much is then the gasoline profit, and then the distillate profit, which is then the diesel and then the jet fuel. Yeah, and then this if you think that this is not worth to check, so you can get like a guesstimate number of your refinery profitability. This is just to recap. So the hydrogen to carbon ratio is also a thing that important to understand. So we have this LPG. Yeah, LPG is then the hydrogen to carbon atom ratio is about 4. Yeah, how do you know it's 4? Right, very easy. It's like LPG. You know that's it's a C3 and C4, right? C3 and C4 alkanes, the normal paraffins. So you can see it's a CN H2N plus 2, and then if you sum them, I mean it's a C3. If it's C3, how much is that C3? Roughly, yeah, C3, and then H8, right? So and then this is then it's not like a 4 as they put it here. So I don't know what this means. So 4 is maybe too much, okay? Because C3H8, and also if you have like a C4H10, right? So it's 2 higher than 2. It's higher than 2, but it's not going to be 4. So this is, you know, that this is then by definition is not correct. But then if you go, but I think the idea of having this kind of graph is that you can see relative, yeah, you can see relative where each products are relative to each other, and then we can see that the coke is very low in hydrogen, very low in hydrogen. So maybe this is maybe like I don't know. This is not mass for sure, but this is also not moles, because moles is 2 plus. Anyhow, so we have coke is over here. It's very it has a very low amount of or low concentrations of hydrogen, and then if it's also like a very high in carbon numbers. Yeah, so you can see here there are two arrows cracking to the left, means from the higher carbon numbers, if you split them or crack them, they will become lighter and lighter in this sense. So if you go to the left, means you are cracking them, yeah, from very long chain to very small, so very long chain. So very long chain, for example, you crack them into pieces. So this is what we call cracking. So you have this one product, and then this another one, this another one. We have like 6 products, so to say, by cracking this long chain. So that's what we call cracking. So by cracking, you will then reduce the carbon number, and then by hydrogenation means you will then give them hydrogen. So if you crack this, or maybe you can then plus hydrogen. So you give them hydrogens, means you will then increase the hydrogen to carbon ratio. This is what we call hydrogenations. So these hydrogenations consist of like hydrotreating and hydrocracking, as we will see later on. At gravity, we have done crude assay exercise. I think I want to cover the refinery configurations, and we have like 45 minutes left, roughly. So yeah, well, you have it here. You can use it for practical purposes, because this is basically the same that I put over here. So if you have like one code like that and another code with a different shape, one code like this and another code like I don't know, maybe something like color, something like this, right? And then so now think with me, So if you have two types of crudes like this and that type, the green and then the blue, which one is the lighter crude? Anybody?
Green.
Yeah,
Green.
green is lighter crude, right? Very easy. And then the red is then the heavier crude, and you will get more like current valuable products like this gasoline and diesel with this green crude. So that's basically what I was going to explain with this crude XA example. So you get it already. This one you can Google yourself, yeah. The corporate ExxonMobil. So you can Google this, and then you will see essays available for download. Let's spend some, yeah, maybe 5 minutes or so. Give it. Crude essay. This open for public, because this is, you can see it here. Let's say somewhere like Malaysian like name. You can have a feeling. Tapis. Tapis. Where's Tapis? Tapis. So you can see Tapis. So this is Tapis. So it's basically the same like what I put over here. Basically the same type of table, but here you can have a lot more options to play with. So it has this specific gravity as well. So 0.8. So 0.8 is then lighter than water, right? And then we can see that the API gravity is also like 42, which is higher than the 38, which is then this is then the light crude. So Tapis is a light crude. So it being a light crude makes it expensive already. Okay. And then the what else? Yeah, it's very difficult. It's all Fahrenheit. It's yeah. So endpoint is about 500 degrees C, 500 to 600 degrees C. Is 1000 in Fahrenheit. So if you calculate that, like minus 32, and then divided by 9, multiplied by 5, you'll get this. So 9 to 5 is about half. So half of this number, which is about 600 degrees C, that's the endpoint. So 600 degrees C something. And then the, yeah, so the light naphtha, heavy naphtha, kerosene, diesel, gas oil, vacuum, and then the residue. You have them all. So you can just glance through. So different kind of condensate. So now condensate. You know what condensate means? Condensate means it's so you from the oil and gas industries you can have oil and then gas. Yeah, oil and gas industry, oil and gas products. So the oil wells and gas wells. So that gas wells, what we want to have basically is only the methane. So we have the methane, and then we get the methane out, and then we have the C2, the ethane. We can then send it to ethane cracker or whatnot, and then we have the C3 and C4 LPGs, and then C5, and then heavier than C5, you get C5 components and C5 plus that you get from the gas wells. We call it condensate. Yeah, condensates. So I repeat, yeah. So in gas wells, which is typically like gas, so the things that condense, that's what we call condensate, which is then the C5 above, C5, yeah, C5 below means, yeah, if you go from lighter to heavier, so C5 below or C5 plus, that's the condensate. So you can imagine, is this heavy or light? Tanggana condensate. Is it heavy or light?
Heavy.
Heavy. Okay, another one. Is it heavy or light? Condensate. In terms of crude oil, In terms of crude oil. Another. Before we go to the assay information. Any other guess? Is it heavy or light? Or all heavy? We'll see. So we can see the API gravity is 73. So it's very, very light. It's very, very light. Because we can see, yeah, it's oil and gas. I'll draw something so that you can be, I don't know. Just make a like very simple one. So you have this oil and gas, then sea bed, sea, and then your reservoir, and then you have this very simplistic. Yeah. So you have this oil, and then you have this gas, and then in some cases you have gas and very much oil, and then in other case you have you have oil, and then you have gas. So these all kinds of scenarios are there, and basically we say it gas wells. It's because it looks like this. This is a gas well, and this is an oil well. Well, roughly speaking, yeah. And then somewhere in between is just somewhere in between. It doesn't really matter. So that gas well, it goes to the plant, and then we want to have the C1 only, the methane, and then we separate the C2, and then C3, and then C4. This becomes LPG, and this goes to steam cracker. This is what you want to sell like natural gas, for your LNG or compressed natural gas. And then what goes here is what we call condensate. So obviously it's coming from a gas well. So this condensate, even though it's condensing from the gas, it's still by nature it's light, it's very light, because it's in the gas phase. But if you have from the oil, we don't see any condensates because if it goes over here to the plant, what you have is this light, which is basically this guy. So it goes there. So it's lights, or some guys at the top. So these lights or gases. And then you have this naphtha, light naphtha, heavy naphtha, and then the gas oil, and then residue. So all of these, they are here. So these what makes it heavy. This is what makes it light. Basically, this is what makes it light. This is what makes it heavy. Yeah, roughly speaking. Where was it? Was I? Okay. Okay. So spent half an hour. I spend more time on the feed because I think that's very important. Because knowing what feeds coming into the refinery, we then have the ability. I mean, we know roughly what to adjust, which unit to push more, which unit has to like a little bit like a slow down. So that we can have most profitable products coming out of the refinery. So if we don't have the information on the feed, there's nothing we can do. Yeah. So that's why companies they put lots of efforts to understand what kind of feed that they are getting, or what the kind of feed that they want to get at how much price, in such a way that they can then optimize the profitability of the plant that they have. Okay, so now refinery configuration, we touched this a little bit already, but just to give you so I repeat the same slides, but I will skip this. Now we go into a little bit more detail, yeah, in this next half an hour or so. So atmospheric distillation unit, we well, it's ADU, atmospheric distillation unit, or CDU, or crude distillation unit, or pipe still, it doesn't really matter. So what really matters is that this is the first line of defense. This is the first unit that any crude oil will have to face in all refineries. So like I mentioned, crude oil, desalter, series of heat exchangers, and then they have this furnace. Yeah, this steam can be there or can be here. It doesn't, or can be there. It doesn't really matter, like this guy. So it doesn't really matter. I mean, depending on your design and stuff. So what matters is that the temperature over here is about, well, I put it here. So it's about 330 C, 385, depending on the this is from the book. I don't see this yet personally, this number. Yeah, what I've seen often is that 330, 340 until 360 degrees C. That's what I've been seeing. But nonetheless, it doesn't really matter. So we need to give all the heat in this and then into the crude oil, and then once it enters this distillation unit, we'll just split into its fractions. There are some steams over here to add. Well, now a quiz. Why do we need steam? Anybody? I just need like one answer, and then I'll move on because we don't have much time. Why do we need steam? Now, so this steam is in chemical engineering term, we call it like to increase the vapor fractions, increase the partial pressure. Sorry, increase the partial pressure of the lights. So that's what it means. What physically it means, just like to strip out. So you have like some lights, so it enters over here, right? So we have this liquid and vapor. This is all liquid, and then we have huge amount of energy put it into it. So we have like liquid and vapors. So some of these vapors are still trapped into that liquid form, yeah, or maybe some of these lights are still in the liquid form. So the use of this steam is just to simply strip out those lights, so it goes up. So it goes up, yeah. So sorry. So you have this one line liquid only, and we have this like two line liquid and then vapor. Sorry, liquid, vapor, liquid. So that vapor goes up, and then liquid goes down, and it's very minor. I mean, it's very small amount depending on your crude, and then depending on the crude, and then depending on the temperature over here. They will then tell how much is then going up and down. So this steam is then to help all the lights that remains in this liquid to go up as well. So we need to recover as much lights as possible. Lights in this case consist of lights, like lights, these lights, and it also consists of this gasoline, and then kerosene, and then all of this gas oil, and so on and so forth. So what is lighter than residue is something that this steam can help us stripping them out. The same goes with these gas wells and then the stripper. So this is what we call like a side stripper. So we have steam to strip out the gasoline, for example, in this case, gasoline, to strip out the gasoline, because this gasoline goes up over here, condense, and become this gasoline. Yeah, that is gasoline. And this one as well. So this is then required to strip. This is then to strip out the what? What does it strip out? So they will then strip out primarily the kerosene part. Yeah, how do we know? It goes up here, and then most likely they will then go up. Sorry, they will go up here and then condense as the kerosene. So majority will be in the kerosene fractions. So you can then fine tune in this crude distillation. You can then fine tune how much steam, or how much. In some cases they use also reboiler. How much steam or how much energy that you want to put into these strippers, so that you can recover more or less of these side streams basically. So that's what we can play around with. And then the above the 15 degrees C above water dew point, so that we don't have the water condense in the system. And also the trays are designed for 80% water. This is very technical, so we're not going to this the 1 meter per second as well. So this is well, we have been repeating this again. So light naphtha, heavy naphtha, some kerosene, gas oil, atmospheric gas oil, and then above 500 is what we call like that residue. So that residue, it goes to this guy. The atmospheric residue goes to the next guy, which is then the vacuum distillation unit. So this vacuum distillation unit, it goes slightly higher, but it's using a vacuum system. So instead of so compared to here, so you have like a air cooler and cooling water over here. It's not mentioned over there. So it's air cooler and then cooling water typically, or only cooling water. So we have this to condense the gases, and then in this case you have a condenser as well, but you then pull the non-condensable using this ejector, as a mean to create that vacuum. So you pull this and then you can then create vacuum. So by creating this vacuum, so this is the typical pressure, so 25 to 40 milligram mercury. Millimeter mercury. So so 1 atmospheric, how much in the millimeter mercury? So 1 atm. So anybody can tell me. So 1 atm, how much? Or 1 bar roughly, 1 bar. How much is that in millimeter mercury? Come on, engineers. This is something that you have to have in your head. Not in Google. So how much is this?
70 something.
760 something. 760 something. 760 something or 760. So this then 1 atmospheric. So now you can tell, so this is about 40 which is then how much is that? So if you divide this by roughly 15, just take 15, divide this by 15, you get this 40/50. So so this one also you divide by 15, and then you get the corresponding atmospheric. So it's very very small. It's divided by 15. By 15. So this one you divide by 15, you get something, I don't know, maybe 0.07, like 7.07, right? 710 kpi, something like that. That very small. And then what was it again? So you can then have the vacuum gas oil, light and heavy. This can go to the next step, which is then the cracking, hydrocracking or coker or something. It goes to either high cracking is either FCC, what we call it. We will see that later on what it means, or you can go to hydrocracking. But it means just like, because this is then long chain. It's all long chain, You remember, the heavier it gets, the longer the chain of the atom number. So we just simply want to have the I know what I forget. So we just simply want to get the gasoline and diesel. What I forget is that say for example, I'll put it here. Where's my thing? I'll put it here. So what I forget is that let's bear with me. So we have the CDU or distillation. So you have this light gases C4 minus. We have this light naphtha. We have this heavy naphtha. We have this distillate, and then we have this gas oil, and we have this residue. Roughly speaking. And then this is C4. That means you know that this is about C5, right? C5 to, I don't know, C8 or something. C8 maybe, or C7. and then this then the C7 until C12, 13, I don't know, and then this then going to be like a C10 until C20, roughly, and this then C15 until C30, I don't know, and then this then C above C above 30, 40, something like that. Yeah, this you can Google this yourself. 15, sorry. So this guy C14, so that means when it goes to the vacuum distillation unit, and this guy is also like a very heavy, like maybe 50, I don't know. Yeah. So where was I with this? I don't remember. Just to give you a glimpse. So it has this like vacuum gas, or and this then that C20 until C40, for example, and then we want to create more of this, right? Because this goes to, I guess, gasoline, and this goes to like diesel, jet fuel, and so on. So it's very valuable products. And then see, this is C7 until C20. What we have here is C20 above. So what we could do is then just to divide this, or crack into C20 a lot lighter, and then so we can make it, we have to make like a C7, C10, or C11, and then C15 to C20. So we have to crack it. We have to crack this guy from having very long C, like 20, for example. This one is 20. So because we want to have it like a 10, because here 7, 10, this is 10, 15. So we want to have it in this range, and then also maybe in this range, and then in this range. So we want to have like two big chunks, because this is then the gasoline, this is then the diesel that we want to, roughly speaking, that we want to make. So out of this this thing, so we want to make this amount of component. So yeah, now this is 10, yeah, something like this. Okay, so if we then divide this, if we assume that this is a very rough approximation, yeah, if we assume this to be like 100%, so we will have like a gasoline in this range, and then diesel in this range, and then some lights in this range. So if the job of that catalyst is then to minimize this, this, and to get more of this, and to get more of that. So that's basically what the job of the catalyst in these two process. Okay. Now after the catalyst, after this guy, it goes to typically this naphtha. It goes to what we call like a naphtha hydrotreating, and then it goes to the reformer to increase the what we call like a RON number. So this RON number, or octane number. So if you go to the gas stations over here, we have like 92 and then 95, and we also have like 97. Do we have 92? We have 95 and 97. We have 95 or 97. And then this naphtha is typically it goes to this. I take this from literature. It has this 2050, because light naphtha, as you know, see this is the C number. So this light naphtha is typically most of them are like paraffin. Yeah. So this paraffin, it has a very low octane number. I repeat, this paraffin is a very low octane number, and this paraffin is predominantly available in the naphtha part. Okay, so what we need to have is a higher octane number. So how do we get the octane number? So things like if we have this, which is the iso paraffin, it has a higher octane number. If you have like a cyclic, it also has a higher octane number. So this octane number, octane number is high. This octane number is also high. And we have aromatic is also highest octane number, but this guy is very harmful to the environment. So we try to reduce this component in the gasoline blend, because we have regulations for that, which I don't remember what that regulation is all about, but we for sure want to minimize this guy in the gasoline. But for sure we will have to make the isoparaffin more. We need to make cyclic more. We need to have the double bond more. So this double bond, the olefins, the iso, the naphthenic, and then the aromatic, they have typically this aromatic being the highest, roughly speaking, octane number compared to the paraffin. So out of that piano, whatever you want to call it, so we want to make more of these guys, and these guys are made in what we call catalytic reformer, in reforming. Yeah. So depending on the type of the feedstock, depending on what type of how much is in the octane number, what type of components that you want to make, you can then use play around with temperature, pressure, and then the type of the catalyst. But this is a typical for the reformers. Yeah, you can. This is platinum catalyst, very expensive. They are, because it's a fixed bed. I mean, it's a heterogeneous reaction. It's a heterogeneous reaction. Yeah, it's a gas phase. They are, because it's a solid catalyst, and then there are some historical or some developments in the reactor itself. So there are few ways to regenerate the catalyst. Why do we have to regenerate the catalyst? Well, ideally speaking, so we make this. Well, we make this olefins. We make this cyclic. We make this aromatics. So what happens? What happens that we are removing hydrogen, basically, right? Can you follow? Because if you can't follow, it's going to be very difficult. Can you follow? Let's make like a very simple. Let's make it very simple. Chemical reaction engineering. So we have, for example, we have C5 or C. Let's make it C8, right? C8H. How much? How much is the H? It's organic chemistry. For paraffin. CH 18. Yeah, CH 18. So this CH 18. So we have like a long chain of C. 1, 2, 3, 4. This is theoretical basis, but with this, I hope you can understand what is happening in the reformer. 1, 2, 3, 4, 5, 6, 7, 8. So this whole thing is 8C, and then you have like H over here. So H3, this is 3, and in between they have 2. Yeah. So you can calculate whole the H. Now into the reformer, this is a very low octane number. Octane number is very low, so we want to increase the octane number. So how we do it? One way is then to make the iso out of this. So you can then, in this case, the iso is the same. Yeah. So the iso paraffin is a CH. How much is then the H? C2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, for example, and you have C. Yeah. So you have C3 is 3. This is 3. This is 3. Yeah. So now instead of you have 2, 2, 2, 2, 2, 2, 2, 2, and then 3 at the end, now you have 1, 2, 3 at the end. See, 3, 3, 3 at the end. But does it make it you? How much is then the H? So we still have the same H, because this C is now only have one H. So this same H 18. So this has a higher octane number, but then the hydrogen is intact. The hydrogen is intact. Yeah, you don't remove the hydrogen. But if you make olefins, in this case, 1, 2, 3, 4, 5, 6, 7, 8. So you make olefins. That means either here or there. Either just put it here. So you have like a H over 3, a H over there. There is also there, and then this is then hydrogen is then now this 1, 2, 3. It's only 1. It's also only 1, right? So you're losing 1 and 2, right? So losing 2 hydrogen, but the octane number is going up, and then plus hydrogen over here. So this is then CH 16. See, this is your organic chemistry. And then if you have like a cyclic, so you have 1, 2, 3, 1, 2, 3, 4, 1. It's very bad at drawing. 3, 4, 5, 6. 1, 2, 3, 1, 2, 3, 4, 5, 6. 7, and that more 8. So you can calculate how much then the hydrogen. Say for example, I just make a stupid cyclic. So 2 2 2 2 2 2 2 2. So you have like a naphthenic C8, sorry, H16 as well. So this is going to make you are releasing hydrogen, octane number going up. So if you have like an aromatic, so you have like aromatic, right, which is 6 plus you have 2, yeah, you have 2. So suppose that you make ethane, for example, yeah, 6, so ethane, and in these aromatics is then C6H6. So we are feeding. Where is that stuff? Where's my mouse? Just to give you, because understanding this is very important in my understanding. I mean, in my opinion. So you have C8H18 coming in, and then you make it an aromatics. You make C6H6 plus C2H6. So how much is then your hydrogen? Now, how much? So you have 6 over here, you have 6 over there. So you are left with another 6, which is 3 hydrogen. So if you make aromatic, you will create a lot more hydrogen. Yeah, theoretical speaking. And this, if you know what is coming in, yeah, you have analysis, you have a composition analysis into your reformer, and then you can then play around with your operating conditions, and then you can then make more aromatic, more isoparaffin, more olefins, and you can then calculate how much then your hydrogen is being produced, how much hydrogen is being produced. Okay, where's my mouse? That's in a glance what catalytic reformer is all about. Okay, you can see it here. No, I see it. You can see it here. So it comes with majority of paraffins. Like I mentioned, and then some naphthenic, and then some aromatics. And then when it goes to this catalytic reformer, you will have a little bit lower paraffins. Yeah, depends also how you operate this reformer. You have somehow you have also a much lower naphthenic, but you will get much more aromatics. And in this case, from the exercise that we just did, from that atom balance, you will know that you will create a lot more hydrogen, a lot more. Yeah, now you understand. So this is going to be a lot more if you have this kind of product slates. And then obviously, because you are making a lot more aromatics, your own number will then be boosted up, going up. Okay, you know what the octane number of toluene or benzene? No, your homework, find how much is then the own number for, or the octane number of benzene and toluene. Yeah, that's the homework. Now, catalytic reformer, I think we don't have much time to discuss on this. I'll just skip this. As you know, that this is basically what we just discussed here. So we're making 3 hydrogen for making aromatic and stuff. And then from alkanes to alkenes, so olefins, you have like 1 hydrogen, and then this is a heptane, and then you make aromatics as well. So even now you have toluenes here, you making a lot more hydrogen. Yeah, because one of the C over here is already like a 4. Okay, so this is what the what scientists have been developing so far to see, okay, what is then the route or the network of the reactions. So we have this normal paraffin goes to a cracked product, goes to this is metal acid catalyst. Okay, so this metal acid catalyst means reformer catalyst that has this metal site, and then it has the acid site. Typically, acid site is done or is used to crack because it's acid here. You can imagine if you put some acid into something, it will just be destroyed. That's the easiest way to memorize it. So you put acid, and acid is then to simply, it facilitates the cracking a lot more. And if you have like a metal acids, it will then facilitate the hydrogenation a lot more. Yeah, so that's the rule of thumb. You just go up here. So so from naphthalene to aromatic, so it facilitates this use this metal catalyst. So it's this facilitates this hydrogen activity. Either you take it, or in this case you are removing it. Yeah, because it goes from the cyclic naphthalene to the aromatics. The aromatic means you are taking out the hydrogen. So basically, I think this arrow is a bit wrong. Yeah. So if from aromatics you go to naphthenes, you don't dehydrogenate that. You are hydrogenating it. So if you go from cyclic to aromatics, that's where you dehydrogenate that. It means you are taking the hydrogen out. You're reducing the amount of hydrogen from the component. So that's basically what it means. So this is then the example of the CCR, continuous catalytic reformer. So in the past they have like a fixed bed catalyst, and then they are now increasing the severity of the reactions, and then they will then see the attritions of the catalyst, and then they use it from fixed bed to like a moving bed or like a semi-continuous bed, and then in this case, this is the latest technology to continuous catalytic reformer. So CCR, continuous catalytic regeneration. So that's the CCR. So the catalyst is regenerated over here, and then it's pushed by fluidizations, goes up and down until goes there. So the catalyst is it's moving like a fluid. Yeah? It's moving like a fluid, and they use fluidization technology in here. So a quiz now. Okay, before, yeah, I don't know if it's a quiz or not. Now, a quiz now. If you can find why is this reactor getting bigger and bigger and bigger all the way here? It's not the other way around, yeah. It enters over here and it's getting bigger and bigger and bigger. So you will find the answer in your understanding of the reaction engineering. You will know why this is done. So I will leave you to that. And then we have the products. So we have the products goes here, the whole products, and then it's being separated. So light gases are then being recycled, and then some gas to gas refinery. The heavy part, which then the naphtha and so on and so forth, goes here, down there, and then being split into the C4 minus, C4 minus, C4. And then the heavy part, the liquid part, the gasoline goes to the gasoline blending, what they call like a reformate over here. Okay. So thermal cracking. So thermal cracking, in contrary to the catalytic reformer, reformer is just to reform. You know that we've seen that it says reformer is just because you are reforming the molecules, yeah, from paraffins to isoparaffins or to naphthenics and so on and so forth. But cracking, as the name entails, is that you just simply crack. I've shown you before. So we just from the long chain, we just crack it. So from that long chain, we just crack it into 3, for example. So you have this 1, 2, 3, and it says thermal cracking, not catalytic cracking, simply because it doesn't use catalytic. It doesn't use catalyst. It only uses heat. It only uses heat. So here we have heat. So saturate with heat, you have saturate, and then the unsaturate and light gas means so we have the saturate, you split into 3, for example, yeah, and one guy is then still as the saturate, the other guy has double bond in it, which is the unsaturate, and then light gases, maybe this one is a bit small, I don't know, somewhere here, something like that. So it's very small, so they become the light gases, and this guy is the unsaturates, this is the heat, and this is the saturate. So this is what it means. And then if you put more heat, means you are now cutting this a little bit more, cutting this a little bit more, cutting this a little bit more, depending on what you want to have. Yeah, the severity and also the feed that you are feeding into. That's basically what this thermal cracking means. So you can then make a whole bunch of kinds of products, like in this case. So gases, unsaturates, and then you can also have coke. So for example, if you cut, what remains is then the things that cannot be cut anymore, which is then the heaviest part, which is then the higher boiling aromatics, which has a very low hydrogen to carbon ratio. This is already very low, and because this is very low, it doesn't look like a liquid anymore. It's just like this like an asphalt, asphalt. So that's that guy. And then if you put into coker, and then you will make coke. So we forget another unit operations over here, which is coker. But basically, coker is a thermal cracking. So that's what the message is all about. Yeah. This is this is then the basically the fizz breaker, one of the unit operations fizz breaker. So the vacuum residue of that vacuum, the residue of that vacuum distillation unit, which is the vacuum residue, you send it to this you heat that to 485 degrees C or 500 degrees C, which you really facilitate the thermal cracking, right? So remember that I mentioned we don't go until above that 360, 370 degrees C. Above that, you will have a cracking. So that's where they do it, here in this fizz breaker unit. So really crack it over there and then flash it. So this coil type of fizz breaker, which is this guy, is a very high temperature, 485 degrees C. It's very short residence times. It's very short because if you put like a longer time, it will then crack even more. If it cracks even more, you will get more gases, which we don't want. That we don't want this guy. We want to have this. We want to have that, because this can be cracked to another operations like FCC and hydrogen cracker. This one you can then send to the gasoline pool blending. Yeah, this one we don't want to have. So that's why at a higher temperature, higher severity, we reduce the residence time. Okay. On the contrary, for the soaker type of fizz breaker, we have like a lower temperature. We have a lower temperature, and then we just let it soak. Yeah, we have some residence time over here, which is higher. Here there is no residence time. You crack it as quick as possible, and then you split it. Yeah. Sometimes you have the quench. This is then the quench. So this is the quench. So from the residue, you just cool it down, and then you just quickly quench it, so that this part, it doesn't have this 485 degrees C. So this is then the much lower than 485 degrees C. So you quench it quickly, so that you can still keep the gasoline and then the gas oil. And here we have like a slightly lower, 30 degrees C lower, and then you have it. You let it crack somewhere here. You let it crack. You let it crack. You let it crack. You let it crack until because it's cracking, yeah. So you need energy to crack it, and then the temperature is then lower and lower, and then you design it in such a way that you maximize the gasoline and then the gas oil. So that's how people design this fizz breaker. Yeah, we know what type of feed that we are going to be using, and then we know how this is the amount that we want to maximize, and then you will then design these units accordingly. This is what they call like a delayed coker. So this delayed coker is just like the same thing basically, but it has to so coker, but it has to then two drums basically. So it's not continuous. It's all discontinuous, but delayed coker is not continuous. Just like it stays in the drum for cooling, hence the name is delayed. And then we have like a 24 hours to fill that unit, 24 hours to fill this guy, fills 24 hours, and then once this is filled, and then you will then fill the other one, and then you let it cool, and then you take the coke out of that. So that's basically what this delayed coker. This one. So you have two drums. So you're filling it in here. Vacuum residue fits. Sorry. This one. Preheat, heat it, and it will then flash. The heaviest one goes to here. You crack it, and then you send it here. You fill this until it's full, right? And once this is full, you will then close the valve over here, and it goes there. And then this one is then being filled, and then you just simply cut the coke, or just use your hammer, get the coke out of this guy. Okay, so that's what this delayed coker means. Now, we have cracked the stream, right? We have cracked them all, but then now we want to increase the octane number in this case, so we use the hydro conversions. So the hydro conversions, there are two types in this case. Number one is then to remove the impurity, which is what we call the hydrotreating, and the other one is then to crack it even more, but using hydrogen. It's not thermal, but we use hydrogen. Yeah, we use hydrogen. Hydrotreating, well, it's the same. How much time do I have? 2 more minutes. So hydrotreating, basically it's removing the impurities. Yeah, we remove the hydrogen, we remove the nitrogen, we remove the oxygen. So in the forms of hydrogen sulfate, ammonia, and then water. So that's basically what it means by hydrotreating. So they are everywhere. So if it's naphtha hydrotreating, kerosene hydrotreating, gas oil hydrotreating, and so on and so forth. Why they are everywhere and they are all very unique? Simply because the feeds are very unique, the catalyst, and then the operating conditions also unique to the type of the feeds that we want to have. You cannot just combine them all together, because the chemistry doesn't work that way. Okay. This is then, yeah, all the study. I think you can go through these slides. The type of the naphtha hydrotreating, I will show you the hydrotreating and the hydrocracking, and then I think we can call it a day. So hydrotreating is simply, because they have the same basic principle. They have like one reactor, and then they have like not one. They have a reactor, and then they have a distillation column. So this is then the reactor. This is then the distillation column. Yeah, this is what I mean. So when you make your model, you need to have at least this reactor and distillation column that comes from this requirement. So it has these 3 beds. So typically, yeah, these 3 beds mean this is then your guard bed. Guard bed means you will then have to remove all of these very big impurities or easy impurities to be removed. And then or maybe you will need to have like how to call it, and then different types of catalyst arrangements, depending on the lessons. So this is only hydrotreating. I was thinking about hydrocracking. So now, and then once you have this hydrotreating, you remove all of the sulfur as hydrogen sulfate, nitrogen as ammonia, and so on and so forth. They will then be removed in this as a purge gas or sour water. Yeah, they will be removed over here, and then we can have the light naphtha and then the heavy naphtha. The gas over here is sometimes because of the operating conditions in the naphtha reactor, sometimes we do a little bit of crack. So we crack it a little bit in such a way, because you know that there is in one of these molecules, the S is over here. So we need to remove this S. So one way to remove this S is that simply we have to cut it. So you have to cut this, you have to cut this, and you take this guy out, right? So you take this guy out as H2S, for example, yeah. So this H2S, it goes here, and then this part that you cut, because you cut this, it goes here. Yeah, can you follow? So that's from the organic chemistry point of view, very rough. Okay. This atmospheric residue desulfurization process. So well, if you go to rapid project, you will see this guy. So that's the only information that I want to share with you. And then hydrocracking. So the difference between hydrotreating and hydrocracking is that hydrotreating is just to remove these impurities, and the main objective, to remove the impurities, and hydrocracking is to crack it, like in this case. So you crack it. I did my mouse. So you crack this. So this one chain, and then you crack it half. So you will get this, and you will get that. Yeah, simply you crack it. But you put hydrogen in it. You put hydrogen in it in such a way that hydrogen will then be a balance. So if you need some more hydrogen into it, so you have the remaining hydrogen over here. So in this case, so you can calculate that. You can do the same exercise that what we just did in the slides before, yeah, when we crack it. And when we do the reformer, so you can also do the atoms reactions over here to understand why is this guy needed over there. Yeah. So this one, yeah, we did the other way around. Um, basically, why we do the hydrogen cracking? Simply because when we crack it, so for example, if you want to crack this, they will become like um, it will lose the hydrogen more and more. So we use this hydrogen to crack simply because we don't want to make coke, or we don't want to make this the reformat or something. So we want to make nice components like these cyclohexanes, like these alkanes, and so on and so forth. So we want to minimize the cokes. We want to minimize these polyaromatics components. So that's when we do this hydrocracking. And that is also the reason why the feeds to this hydrocracking is one of the heaviest feeds that is available in the refinery. So you can see here. So it goes to the hydrocracker. This one is then from the residue goes to the hydrocracker as well. Yeah. So this is still can be cracked. They still have a long molecules, but we need hydrogen to minimize the formation of the coke and stuff. I think I'm over my time already. Do you have at least one or two questions? You can go further. So yeah, it's all kinetics and stuff. So we have now we are on like a slide of 34, and we have like 89 slides to go. But I know that we are not going to make it. Nonetheless, you can go through this FCC and then hydrocracking and so on and so forth. This is just an intro. You have to read it yourself. And then if you have any questions, we have this WhatsApp group, so you can just post the questions over there. So if I've sometime I will look into that, I will then reply to your questions. There are many stories over here, which I don't think I have enough time. We have enough time to go through this in one session. So yeah, 2 or 3 hours. Like I said, this is like one semester in itself, and then understanding it requires you another month to do so. So nonetheless, all the materials are there, all references are here. I will take one question and then we call it a day. Any question? Okay, yeah, you have been sleeping already. Yeah, I know that. It's it's a Sunday afternoon, right after lunch. This is a strange subject. It's a perfect time to sleep. Any questions? One question? No. Well, again, you are the one who going through this course, so I think you need to make sure that you yourself as get some knowledge in here through the course as well, because for me, the more I share something about this, the more knowledge that I have, right? I mean, that's the only thing. So the only thing that doesn't go away is knowledge. So so you have to get knowledge. If there is no question, I know that I'm going super fast, simply because I have a lot to cover, and we know already from the beginning that it's impossible for us to understand the refinery in only like 2 hours. But again, this is just like an introduction to refinery. You have to read a lot more, and then you can then by doing so, you may have some an idea on what projects that you are going to do. I think it's going to be like an individual projects. Yeah, if you may wonder, I need to make it like an individual project. So you have to think about what type of plant or which part of the refinery that you want to model. It has to have at least a reactor and a distillation column. Yeah, one reactor and then one distillation column. That's the bare minimum for that simulation model. So we will use that simulation model as your plant, Okay. Use like a simple kinetics for that. Yeah. Don't use conversion reactor for your to calculate your reactor, to calculate the reactions. You don't use the conversions feature. Use a kinetics, a simplified kinetics model. Okay. What else? Yeah. Yeah, like I said, if you have any questions, post it in our WhatsApp group. Anything else, Afik, that you want to add? Otherwise, we can just close
I
this.
think, yeah, I think they need sometimes to digest. But I also believe that the refinery is also one of the core subjects. So
Yeah.
I don't know if they have went to this subject or not. But otherwise, they will learn more details on the refinery on that subject, the core subject. Yeah.
Yeah, exactly.
All right. So I think if nothing, I think we can stop here. So